out the meaning first. So blank page in your notebook, or it doesn't have to be blank, next spot in your notes. Write this down, and then get this in your calculator. And the time period we are interested for this particular one is t equal 10 minutes to time equal 15 minutes. Yes. So it's in terms of time, you use X on your calculator, but write this down and then get on your calculator that equation, graph, so that your should end up looking like this. I'll give it up for you. Hold on. One quick thing. Every eye's on the board. Look up. So this is a feature of the 84 and the 83. The Inspire has something similar. I just don't quite recall how to do it. You can actually enter multiple equations, and then if you don't want certain equations to graph, you simply highlight the equal sign like I have highlighted here. If I press enter, that graph is now selected. If I press enter again, the graph is not selected. I don't want to graph this one, so I've turned it off. I only want the top one. And I'm going to window 0 to 15, zoom fit. So get this on your screen as soon as it shows up, and then in your notes as well. So can you go back to the 1 second. Let me just copy this over.
So if
okay. Question?
If our the 0 x-axis doesn't show again, what do you recommend?
So what I do if I don't see the x-axis is under y equal. I just set one of the y equals to 0. Any line y equals 0 is the same as the x-axis. Good question. 2 points for Kate. What I did, Laura, is it wants me to go from time 10 to 15, but I don't like not being able to see the vertical axis, so I went from 0 to 15, and then zoom fit. Is that your question?
Yeah.
Okay. So you should end up with that on your calculator. I'll just walk. If you have a question, just stop me as I'm walking. Get that on your calculator, get that in your notes. Yeah, it's 82 plus 4 sine of 2.
So it's just x over 2?
Yeah, x over 2. We think of it as t, but we're using Hey, look up, please. Hey, raise your hand, please, if you have this on your screen. Show me hand. Who has this? Who has this on their screen? Mark down an extra credit point. Questions? Hey, look at me. Hey, watch. We're going to use integration for something else. In fact, you should have this in your notes. If you don't, then I would add it to your notes. Right here. We talked the other day that when we talk about integration, all we're really doing is we're just multiplying over and over again, and then we add them up. That's what integration is. That should be in your notes. I had you make a list of different uses of integration. And one use was if we integrate velocity, we can calculate the change in position of a moving particle. Recognizing that change in position is really the same thing as just subtracting the two different positions, we figured out that a second use of integration is to actually calculate the position at, say, time 8. Or we can rearrange a different way and calculate the position at time 3. Any questions on any of that? We also said that if we never make the velocity negative, then we're just kind of adding up our steps, which means we're finding the total distance traveled. So that was the third use of integration. The homework last night has a fourth use, how to compute the area of some odd shape. Okay, today I'm going to introduce a fifth use. We're going to use integration to find the average value of a function. So add this one to your list. And you can write that down, and then I'll explain where that comes from. So we're going to use integration to find the average value of some function. That's kind of small. Let's make that bigger. So right here, average value. Oh, very good. So what I wrote here, Paris, 2 points, is we talked about, and you used it on the pink packet, every time you were asked to find an area, you were literally finding the function or the y coordinate at the top of the region and subtracting from that the y coordinate at the bottom.
Oh, top and bottom.
That's a good question. Make sure your cell phone is put away. Anybody else? Okay, good. Don't forget this either. You'll need this in the homework tonight as well. 2 different ways to compute an integral. You know the 4 different Riemann sum methods, and now you've been using your calculator to compute an integral. The calculator actually is doing something very similar to a Riemann sum. It's just adding up the area of a whole bunch of different rectangles. Any questions? Okay, so we're going to investigate why this works real quick. How to find the average value of a function. So you have written on your paper this formula. Write this now, please. If we were to integrate from, say, time 10 to time 15, and we're integrating f of t dt. Okay, we talked about the calculator using a dt of about 0.00001. Okay, that's hard to think about because the numbers are so small and there's so many numbers. So for a minute, we're going to just talk about dt being something easier to conceptualize. We're going to let dt be just 0.5. Write that down. Just going to watch your pencil, make sure you keep up with the notes. Watching pencil. when the integral actually occurs within the calculator, basically what's happening is the calculator takes this value, so this integral is going to end up doing this. It takes this value and plugs it in for t. So we're going to write down f of 10. F of 10 is this y coordinate. See, here's 15. There's 10. So it's finding this y value right here. That's f of 10. We then multiply by dt, which would be 0.5. Okay? dt literally means the change in time. So we started with a time of 10. The change in time is 0.5. So easy question for extra credit. Raise your hand if you can tell me what's the next time that we would be plugging in here. Hands up, everybody who knows. Come on. So we plugged in 10. That's because we were told to start at 10. But time is supposed to change by 0.5. So what's the next time value that we're plugging in? Okay, everybody who has their hand up. What does it suit on? How many knew that it was 10.5? Point. So this becomes f of 10.5. And then we multiply that by the dt again. So really, look at it. It's related to area because f of 10 is this value. 0.5 is the width. And so we get a rectangle that's very narrow, kind of like this. Then we go to 10.5, which is this value. Change color. We get another rectangle, like this. Question, please. Go ahead.
So the rectangles are 0.5 apart. Are they not? I thought they were always 0.0001.
Outstanding, 2 points. So inside the calculator, the default setting is the 0.00001. But when I try to write that down on paper, it gets really cumbersome because it's such a long decimal. So we're using 0.5 to make it easier to write, but the concept doesn't change. That's all. So we're just kind of using it temporarily.
Okay.
So really it is the smaller value. Does that help?
Yeah.
Good. Anybody else? Awesome. Okay, the next one. Just easy extra credit. Go back to the blue, sorry. Raise your hand, please, if you know exactly what I'm going to write next. Okay, everybody, come on. What am I going to write next? Everybody knows. What is it, Dawson? 11. F of 11. And then multiplied by what, Dawson? 0.5. Ah, shoot. Multiplication would be better. Okay, please raise your hand if you knew that's what Dawson was going to say. Point. Any questions? Okay, it's a little bit tedious, but I want you to write out the whole string. But there is, because I need you to see something. But be a little cautious. When we get over here, the last value is actually going to be, leave enough room for this. So the last value is going to be f of 14.5 multiplied by 0.5. Because that last value here creates a rectangle that covers the remaining space. So we don't really ever have an f of 15. We just go to f of 14.5. So write down on your paper all of the terms to here. I'll walk around if you have a question. It's a little bit tedious, but just do it quick so we can talk about it. Write it down too. a little bit tight on my space here. Just watching your pencil and asking questions.
I'm just wondering, like, it looks almost exactly like the Riemann sum, like how we put it in. But then in the Riemann sum, we don't have the f, like the 10.5 times the point, like the f of the times the y. We have the f in this one. It's like the same concept.
2 points. It actually is exactly the same. The only thing you're not seeing is that when we did the Riemann sum, we just found this y value because we had a table. And so we would just write down that y value. But f of 10 means the same thing. Does that make sense? So yeah, no, this is actually the left Riemann sum. Like you're looking at the first subinterval as being from time 10 to time 10.5, and we're picking the value of the function on the left. It's a left Riemann sum. It's perfect. Please, Sugan.
Could you explain one more time?
No one talking, can't hear.
Just one more time, why we're not doing left 15?
Oh, gotcha. So the idea is that we go for the first subinterval, which is from 10 to 10.5. And we're using the value of the function on the left of that subinterval to represent all the values in between.
Oh, okay.
When we get to 14.5, we use the value on the left to represent all the others. So we don't need the 15. Please.
So it doesn't include start with 10.5.
Yeah, 2 points for Aaron and Suganda.
And then it would go
All the way to 15. It's perfect. So what Aaron just said was, this is a left Riemann sum because we're always picking the value of the function on the left of every subinterval. If it were a right Riemann sum, we would not have chose f of 10. We would have started here and gone all the way to f of 15.
How did we know for sure that this is supposed to be the left or not?
Oh, I just picked that.
Oh.
Yeah, that's just an example I took.
Why can't there be like one where you have all of them?
Gotcha. Okay, everybody, eyes on the board, everybody. I want everyone to be able to answer Sugana's question. 2 points, Sugana, it's very good. Okay, I chose dt to be 0.5. Paris mentioned that in the calculator we think of dt as being 0.00001. Okay, easy question, just extra credit. Raise your hand if you know what dt really should be ideally. Like, what do we want dt to really be to get the most accurate computation possible, theoretically possible? What is dt supposed to be? What do you know? If you don't know, talk to somebody who knows so you can get the point. Like, what's dt supposed to be so that we can get a perfect answer? What's dt supposed to be? Very nice. No, it's good. Don't worry at all. Hey, hands up. Who knows? Who knows? Come on. What's dt supposed to be? Chelsea?
Smallest numbers like 0.00 keep going to infinity.
Yeah, it's hard to conceptualize that, but really it's infinitesimally small. So it's like thinking of a number that's 0.00000, somehow whatever forever means, and then there's a 1. How many knew that? Come on, 2 points. Okay, look. Listen to Sugana's question. Hey. Okay, so that's really the only way we ever get all of them, is that the interval is so small. That kind of help a little bit. It's hard, honestly, Sugana, it's hard for me to think of that, but that's the idea. Okay, look at me. Okay, look here. Okay, we are doing what I said integration is. Notice, multiplication, 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 and then they're all being added up, right? Okay. However, because dt is the same value everywhere, we're going to do a little trick today we've never done before. It's not a big deal, I just want you to see how this works. Because dt is the same value, we can factor the dt out of this big long summation. So we could rewrite it like this, and I want you to write this on your paper. We can say this is all the same thing as being, hold on. We'll take a little shortcut so you don't have to write so much. It's really f of 10 plus, we'll just say dot, 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 all the way to f of 14.5. And And then all of that is being multiplied by 0.5. We have simply factored the 0.5 from the big long chain. Watching your pencil. So write that down. And just factor the 0.5 from that big long chain of numbers that were being added up. So show me 1 to 5 how comfortable you are that the blue and the green are exactly the same. Right? There's no difference. If you're uncomfortable, show me 1 or 2 or something. But show me how comfortable you are that it's really the exact same thing. Checking everybody. Give yourself a point. Good. Okay, look up. Hey. So inside the parentheses here, we're just adding up the values, right? We're just adding them up. Okay, I'm going to throw in a number. I'll explain where the number comes from in a second. Just kind of trust me for a minute. So new color here. I'm going to take this, f of 10 plus dot, dot, dot. I'm creating something new here. That's why I did not put equal. Creating something new. I'm going to take that chain, and I'm going to take 0.5. I'm going to divide 0.5 by, let's see, we went from 10 to 15. So I'm going to take 15 minus 10 here. You write that down. It'll make sense in a second. Just stay with me. Now that is the same as, it's a bit of writing because of all this stuff, but so now we have this, f of 10, subtract, oh wait a minute, hold on a second, my bad, I read myself. So, f of 10 plus, dot, 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 f of 14.5, and basically, this is getting multiplied by 0.5 over 5. And I appreciate your patience in rewriting it. It helped make sense of it. So get that written down, just watching your pencil. Okay, now look here. Look what I'm showing. Like eyes up here, eyes here. Look at this. Okay, I want you to. The easiest way to think of what happens next is this fraction can be written as a simpler fraction. Like it can be written as 1 over something. And the way that works is you're just thinking of like how many 0.5s are there in 5. So you all know that. Just say it out loud. How many 0.5s are there in 5? 10. So this fraction is the same thing as 1/10. Agreed? Nod, does that make sense? Okay. So this is all equal to the red. Basically 1 over 10 multiplied by f of 10 plus dot, 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 f of 14.5. Okay.
Wait, why are we dividing it?
The y I haven't explained yet, but it will in a minute. So all I've done is I introduced this division. You don't know why I did it yet, so don't worry about it. It's a good question, Allison. It's your point. That gave me this fraction, Allison. And then I just said this fraction could be written in a little bit simpler way as just 1/10.
Okay.
Okay, are you with me? The next one for bonus points. If dt, well, let's still do that. Let's look here. Okay, raise your hands, please. How many terms are being added up in here? Just raise your hand if you know. Like it's written down up there if you want to count them. But how many terms are we adding up here? Raise your hand if you know. Just count them if you don't know. 1, 2. How many are we adding up? How many are being added up? Show me your hand. Oh, you guys are smart. I like that. Show me with your hands how many we're adding up. Very nice. Yeah. Dawson's like, bring it on, man. Bring it on. Let us, put it down. 1 full ticket. Cool. Write it down. So write down 10 tally marks, 1 full ticket. Way too generous, but it just could not resist the temptation. It says I didn't really plan that, Dawson. I expected you to go like this, and then you're like, hey, look. Well, I just thought you'd raise your hand, like to just answer the question. Suddenly people are going, well, there's this many messages. Okay, I really dumped in. Okay, moving on. Hey. Okay, there are 10 terms. We're adding up 10 terms, and then we are dividing by 10. Okay, raise your hand if you know the word for what we just did. Like, hands up, come on. What's the word for the mathematical operation we just performed? We added up 10 things and we divided by 10. What do we do? What do we do? What happens when you add up 10 things and you divide by 10? What are you computing? You add up 10 things and divide by 10. Hey, what are you computing? Hey, how many knew that was the average? Show me. Point. Look. Hey, why? Okay, so without telling you that's what we were doing, that's what happened. But look at it. It's really very interesting. Hey, look. We did an integral, right? We did an integral. Multiply, 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 add them up. All I did was rearrange the computation a little bit by factoring out the dt, right? So in green, we haven't done an average. We've just done an integral. Got it? That makes sense? Okay. So in green, we've just done the integral. The next thing I did was I said, hey, let's just, okay, I said it was random. I knew what I was doing, of course, but you didn't know. I said, let's divide by the width of the integral. This integral is from, well, this is like the coolest thing ever. Hey, the integral was from 10 to 15. That's what I did. I divided by that width. From 10 to 15 is a width of 5. So I divided by that width. That got me to here. A little bigger. Right? You still can't quite see that it's an average. But when you change the fraction into something easy to understand, look up there, now you can see that it's an average. Okay? Show me 1 to 5 how comfortable you are that this really is the average. Like it worked perfectly. We found the average of those 10 things. Mark down a point. Okay, keep watching. Oh, please, Ken, please.
How did you know to change the dt to 0.5 then?
So the 0.5 is a random example. And we couldn't show,
Yeah.
what's it again?
It was like perfect.
Yeah, but let me show, you're right, you're on the right 2 points. Watch me, watch me, watch me. Everybody look up, look up. Okay, I chose 0.5 and just say it out loud, please. With 0.5, how many samples did we end up with? Say it. 10. Okay, if I choose 0.25, 0.25, how many samples will we end up with? Say it. 20. Watch the numbers here. Over here, this doesn't change. Look, oh, this is so cool. Look at this. This isn't going to change. Okay, one second. No. Okay, look. Yeah, have I told you the story, right?
Yeah.
Okay, good. Okay, so, I'm serious. Don't let me get too excited. Because this is how it happened 2 years ago. I'm serious. Hey, look, 15 minus 10. Is that? It actually was a different one, but close enough. This is really good. This was Ethan, this was the same feeling. It was the exact same feeling that I'm feeling right now. And that's where the excitement kind of overboiled. Calm down, breathe. Okay. Look, okay, you just said there would be 20 samples, right? 20. But 15 minus 10 doesn't change. It's still 15 minus 10. So check out this number. So the dt would be 0.25. Watch over here. Let's change color to not mix it up. Yeah, you can see it. Look, you'd have 0.25. It'd still be divided by this. 5, right? Okay, say it out loud, please. How many point? You don't know, do it on your calculator. How many 0.25s are there in 5? 20. This is the same thing as 1 over 20. So here's Kenneth's, look, 2 more for Kenneth. It's the perfect question. I chose 0.5, and we ended up with 10 samples divided by 10. But if I had chosen 0.25, okay, if I had chosen 0.25, we would have ended up with 20 samples, and we would have divided by 20. So the 0.5 was random. It didn't matter. Does that make sense? Please, Kate.
So why don't you just choose like 1 so you don't have to write it out so many times?
Oh, awesome question. 2 points. Awesome. Hey, look up. Look up. All of you answer this. Look at how we did the integral. If dt were, sorry, this is way too expensive. If dt were 1, look. If dt were 1, listen. Come on, focus. Hey, look up. If dt were 1, you'd plug in f of 10. Just say it out loud, please. What would the next f of what would it be?
11.
How many terms would you have? 5. Look over here. dt would be 1. You'd be dividing by that, right? You'd have 5 terms you would be dividing by 5. You see the pattern? Okay, here's the thing. I could have chosen dt to be 1, or 0.5, or 0.25. But in reality, the goal of this discussion is to help you understand how to find an average value of a function, when in reality, how many values are there really between 10 and 15?
Infinite.
There's an infinite number, okay? So we'd like to have dt be really, really small. But if you just keep following the pattern, it works perfectly. 0.25, we end up with 20 samples, right? If you just keep going, you get smaller and smaller dt and more samples, but the computation always works. You always end up dividing by how many terms you have. Mary?
So if the computation is like the same, no matter how many different like numbers you have, can you pick the highest dt you possibly can?
Outstanding. 3 for Mary. So write this in your notes, please. Write this down. Write this down. Average value of f of x, so any function, or, and we'll just use this example, x equal 10 to x equal 15. It doesn't really matter. This is good enough for your notes. Here's what Mary just said. Look. The formula is exactly the same. It doesn't matter. We always take 1 over the 15 minus 10, the width of the integral. We integrate from 10 to 15, whatever we're trying to find the average of. That parentheses to the bottom. Like that. That's going to compute the average value of any function. Like Mary said, this formula works regardless of what you pick for dx. That's what we just showed. So you could pick 1, you could pick 0.5, you could pick 0.25. You could do like Mary said and pick this to be really, 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 really small. You'll still get a perfect average.
So it'll be the same every time, even if you pick 0.5.
Oh, stop there. Somebody can answer that. So the question was, I can make dx whatever I want to get an average. But if I pick 1, how many terms am I adding up? Say it. 5. If I pick 0.5, how many terms am I adding up? 10. So are the averages that I compute, are they all going to be the same or different? Say it. Different. Which is most accurate?
The smaller
The
one.
smallest. Which one takes the longest?
The smallest.
The smallest. That's the trade-off. Oh, so on the AP test, what they do, hey, listen. So on the AP test, what they do, and you'll practice this in the homework tonight, is many problems, they say, hey, compute the average just using your calculator. And so the dt that you're choosing, the dx that you're choosing is really just the 0.00001. You don't worry about it. Just type it in. But sometimes they say do it with a Riemann sum, which means your dx is much larger. But you don't have to worry about any of that. They'll just tell you to do it. So they'll tell you which dx to use. So everybody's answer comes out the same. So, other questions? Please, Mary.
Wait, how do you plug it into your calculator if you have so many different like numbers like f10?
Oh, gotcha. So you don't worry about plugging in all of this. I just wanted you to make sense of the idea.
Okay.
You just plug in the integral. When you do the integral, it's doing all of that for you. Please.
Why are we dividing by the difference?
So look back up here. The integral alone only got us to here. Like adding up all the terms and multiplying by dt. The next line, notice there's no equal sign from here to here. So I introduced a new idea. I said, hey, what if we do the same thing, but we divide by the width of the integral? What's going to happen? When we traced it through, like, oh, wow, that's almost magic. We changed from just being an integral to being an average.
Oh.
That's what it is.
So for the Riemann sum, like if it asks you to do Riemann sum, you don't do that on your calculator, right?
Correct. You do it term by term because it's Riemann sum. But yeah, please, Dawson.
So keep doing a Riemann sum, like would this be on the written portion of the AP test or not?
Okay, everybody, eyes up here. Eyes up here. Look up. Everything I've shown you on the board here, none of this is showing you like how to solve a problem. This is trying to help you understand why this works. Does that make sense?
Yeah.
Okay, how we solve the problem is, let's go to the yellow sheet now. Go to problem 1. Actually, we'll jump to 14, I think it is. So go to 14 on the yellow sheet. Go to 14 on the yellow. Yeah. So go to 14 on the yellow. Okay, they say traffic flow is defined as the rate. Okay, you should get in the habit of circling the word rate. Makes a huge difference on the AP test. To keep track of when are we talking about a rate and when are we talking about quantity, like how much. So traffic flow is the rate at which cars pass through an intersection. So I'm literally trying to kind of envision this. I'm thinking, okay, I have an intersection, and they're talking about cars going through the intersection. So they're counting them going both ways. Measured in cars per minute. So units are super important. Get points for them. Cars per minute. And they say it's modeled by this formula. So that's what we graphed on the calculator. So this is telling you different cars per minute. Like if I go to the calculator and hit the graph and I hit trace, I could type in time 10, and I would see that at time 10, roughly 78 cars per minute are flowing. It's not 78 cars, 78 cars per minute. So that means if you stand at the intersection and watch, and you can somehow count both ways carefully, after a minute you would have counted 78 cars. That's the rate question. Awesome. Okay, so this is a bunch of different rates at different times. I can go to time 11, and the rate is now different. Okay? Any questions about that? Awesome. Okay, so back to 14. The question says, what is the average value, keyword right there, the average value. What is the average value of the traffic flow? Converting that, they're telling me to do this. Find the average value of a capital F is the traffic flow. So I'm trying to find the average value of capital F, and the time interval they want is t equal 10 to t equal 15. That's what they're asking me to find. So the discussion we just had tells me how to do it. I'm going to take 1 over the time period, 15 subtract 10, and I'm going to multiply that by the integral from 10 to 15 of whatever it is I'm averaging. Since I'm averaging f of t, that's what I want to multiply by. Because we just went through an example showing how if you do this, you actually do get an exact average, depending on the size of dt. But as Peyton said, because they're letting me use my calculator, I don't have to worry about choosing dt. I just go with whatever the calculator chooses, and I get a very accurate average because it's going to add up about 5 million terms. Okay? Pretty good average. Please, Chelsea.
Do you always do, is it always 1 over the change time?
Yep, that came from right here, Chelsea. When we were kind of, how would I say, figuring out the formula. When we were figuring out the formula, we started with the dt over 5, but that reduces to just 1 over how many we have. So the combination of this and the dx are working together to give us the right number. Does that make sense? Please, you got it.
So why would you put x instead of 1? Like x over 15 minus 10?
Oh, look back up here. Okay, this is the dt value. This is the width of the time period. So this can be different. This won't be different, but they work together to make sure we end up dividing by the right number. That's why we don't put 1. Or that's why we don't put the x. It's really right here, what's happening is this value, dt, is working with this value to come up with the right number for the denominator. Anybody else? Okay, so all that's left to do now is just type it in the calculator. So I can move this over a little bit. So this is going to equal, okay, on the 84, and also on the Inspire, please don't ever type a fraction using the slash. Always use the fraction key. So if you don't know where that is, I'm going to hit alpha, y equal, choose number 1. That gives me the fraction bar. So it's 1 divided by 15 minus 10, multiplied by the integral, so that's math 9, 10 to 15. My f of t happens to be in y1. Alpha y equal. Alpha y equal. Yeah, the 83 won't do that.
Yeah.
So you're stuck with using the fraction bar in parentheses. You have to just be careful. So. Hold on. It's the first one. What's that?
How'd you get that one?
Alpha trait. Anybody else have a question? Please.
Yeah, you have to do that. You'll be fine. In my house in Florida.
Hey, look up. Hey, look up. No one talk, everyone look at me. Okay, please, look at your paper and notice, let me show you how the scoring works. This problem, I believe, is worth 3 points. They gave 1 point if you had written on the paper this. Now, if you write 1/5, it's fine. I write 15 minus 10 to remind you of the formula. So if you have this and the limits, that would be 1 point, okay? If you have the correct integrand, like what's supposed to be integrated, so you've got capital F of t dt, that's the 2nd point. Then if you have this with units, you don't have the units, you lose the point. Then you get a 3rd point.
No matter whether or not we specify that.
No. The AP test, if you're using your calculator, even though it still is an approximation, they'll usually write equal. Yeah. Please.
Why is it capital F?
Oh, just because they chose capital F.
Oh,
That's all. So you just have to match what they chose.
okay.
Anybody else? Okay, how many have this written on the paper? All of it. Show me. Point. Full. Okay. Go to problem 1, please, on the yellow sheet.
So that was using a calculator.
Yeah. The only difference is, hey, this is a Kate's question. It's really good. I'll flip back. You don't have to. Watch. It's a really good question. Look at me. Look at me. Okay. If they had said find the average and then compute that average using a, say, trapezoidal Riemann sum, I would still have all of this written because I've got to do the integral to get the average. It's Riemann sum is the way I find the integral. So in your brain, hey, keep those two things separate. There's what you need to do, like you're making an integral to accomplish something, and then there's how you will compute the integral. That changes from problem to problem. If they ask for average value, the first part never changes. You're always writing this. It's just how you compute the integral that changes. So I'll see no problem. Just make sure. Anybody else? Okay, back to 1. In problem 1, they're showing a table. Okay, look at the units. Like, get used to seeing units. Gallons per hour. So this is a rate. It's not an amount, it's a rate. They're saying at time 0, there's a pipe, and you can see the water coming out of the pipe. If you put a bucket into that pipe, in 1 hour you collect 9.6 gallons. Okay? It's not flowing very fast, it's pretty slow. It takes an hour to get 9.6 gallons.
Or is that how much is already in the budget?
No, this is a rate. This is a rate. If it were how much is, if it were an amount, it would say at time 0 there are 9.6 gallons. So there's a pipe. There's water kind of trickling out of it. It's not coming out very fast actually, it's coming out pretty slow. Slow enough that if you put a bucket under the pipe and you wait an hour, if the rate never changed, you'd have 9.6 gallons. It's a big bucket. You see the difference between amount and rate? Yeah. Okay, please, Eric.
Why wouldn't it just say at 1 hour it's 9.6, then at 0 hours?
Oh, they're just showing you that over a 24-hour period, it's like right at the beginning of the period, like we say we're going to start right now. Let's look at the pipe and we see water trickling out of it.
So at 0 the flow is.
Yes, at 0 the flow is. So at time 0 the flow is this rate. The rate is increasing, for sure. At time 3, okay? At time 3 you see more coming out of the pipe. Still just a trickle. It's a slightly larger trickle. Good question. Anybody else? Awesome. Hey, look up. So that's R of t. as you read the problem, they describe another equation, Q of T. They say the rate of water flow can be approximated by Q of T. All that means is they created a, look, this is a measurement. Don't talk, focus, come on. This is a measurement. It's like they really went out to the pipe and they said, hey, at time 3, we can measure the water flowing at this rate. They put a flow meter on the pipe, it measures that amount. Some mathematician takes all this data and he creates an equation that doesn't match this exactly, but pretty good. Okay? Like, for example, everybody put that in your calculator. Go. Come on. You're going to need it in your calculator anyway, so put that in your calculator. Steven, you get yours to work. I'll be back. Get your mode back. What mode are you in? Okay, I'll be back in a minute. So don't delete what you have, Steven. I don't want to look at it. Gary?
Oh, but we essentially don't need that, like, table. Like, it doesn't really serve any purpose to us. If you
I'll
have an
explain
equation.
why in a second. Yeah, get the equation entered. And the time period is 0 to 24, so you want a window 0 to 24. Alpha and white. Right, zoom 0. Zoom. 0 to 24 because it said a 24-hour time period. Eric, a question? Steven? Okay, look up again. Eyes on the board. Hey, look up, come on. Raise your hand if you have this on your calculus, come on. Raise your hand if this is on your calculus. Show me your hand. Who has this? Keep going. Show me who has this, come on. Several points. Watch. Don't talk again, come on. Quiet. No one talk, no one talk. Okay, look up, okay, look up. Okay, look, this is the equation for what they're calling Q of T. If I hit trace, and I type in, let's don't do, time 12 is fine. Look, oh, I don't like that, hold on a second. Mode, for this class, it's better to see decimal approximations. So I'm going to change the answer thing here to decimal. Second quit, graph, trace. Hey, look. So this formula, hey, formula gives me 11.392. The table said at time 12 it should be 11.4. That's why this is just approximating the table. This is pretty good. Agree with me? Let me answer Mary's question. Look. On an FRQ, they give you information. That's to look up. They give you information. Then they ask questions. I have not shown you what question A and B were, because we're just kind of building, right? A and B likely included the table, Mary.
Oh, okay.
Does that make sense?
Yeah.
For example, as long as you've asked, let's write something down here. You'll need this in the homework tonight. Like a common question involving the table would be this. Estimate, write this in your notes, write this on the paper. estimate R prime of 12. Come on, write it down. Write it down. Estimate R prime of 12. Okay, so I'm giving you, look, at me, eyes on me, eyes on me. The one thing I'm trying to teach you all is really how, okay, every college class I ever had, this is how it works. You either go to class and you focus like you have never focused before, or you just don't go to class, and then you try to figure it out on your own. But you have to figure it out somehow, okay, or you fail and you lose all your tuition. That's how it works. Okay? Life. But look, some of you got to break a habit. You focus, then you tune out. You focus, you tune out. You focus, you tune out. And you miss things. You got to stay with me. Stay with the train of thought. So I'm showing you an example that's going to occur later in the packet. It's not this problem, but it's going to happen. So I'm just using this table to show you. A problem later in the packet is going to give a table like this, and it's going to say estimate R prime of 12. Okay, one person, please. What does R prime of 12 mean? Like, here's R. What does R prime of 12 mean? Please. Very good. R prime of 12 means the tangent slope of R at 12. But you memorized last term that you can't calculate a tangent slope from a table. So instead, we use a different kind of slope to approximate the tangent slope. Raise your hand if you remember the name of this other type of slope. Come on. Oh, you know. What's the name of this other type of slope? You did it a lot last term. Other type of slope that we use to approximate a tangent slope. Jake, what is it? How many knew it was secant? Point. Watch me. Listen. Hey, don't tune out. Come on. So if they ask me to estimate a tangent slope, I'm going to do it by finding the nearest secant slope. But for 12, there are actually three possibilities. I could go before, like from 9 to 12, that's a nearby secant. I could go from 12 to 15, that's a nearby secant. Or I could really do the one that kind of jumps over, the 9 to 15. Any of those are valid. Just choose one and do it. They'll give you credit for it. Okay? So for example, if I choose to do the one that jumps over, I'm going to say R prime of 12. I would write this in your notes. Is approximately R of 15, that's the Y2, subtract the Y1, R of 9, all divided by 15, subtract 9. And I would just figure out whatever that is. Turns out that's 11.3, subtract 11.2, and all that gets divided by 6. The units of that are going to be gallons per hour, because the units of the numerator are gallons per hour, the units of the denominator are hours. It's because R is already a rate. So we're finding a rate of a rate. That's why we end up with units like this, gallons per hour per hour. Question? Please, go.
I'm curious where like the R prime came from and what the equation was that we used for R of 15 minus 1.
Gotcha. So what I did is I said, hey, I'm trying to get you ready to be able to do the packet when you get home. This is not asked on this problem, but it is asked later in the packet. So I made it up. I said, hey, they're going to ask you to estimate R prime of 12. We recognize that R prime means the tangent slope of R at time equal 12. But we don't have that. We have R itself at time equal 12. So we can't find a tangent slope from a table, so instead we do a secant slope. Secant slope is the type of slope you've been calculating for years. This point minus this point, y2 minus y1. So that's what I did. Here's the y2 value right here. Subtract the y1 value right here. Divided by x2 minus x1. There you go. Please.
Could you write it as gallons per hour?
Yeah, same thing. Any questions? You'll need this for the homework. Okay, if they asked you to do this, now look, if there were 3 ways you could do this one, 3 ways. If they asked for this, they say estimate r prime of, oh, that's a terrible r. Say they say estimate r prime of, I don't know, 10. Look over here. Now you only have one option. You don't want to go from 9 to 6 because that doesn't even include 10. You don't want to go from, say, 12 to 15. That doesn't include 10 either. The only thing you can calculate is going from 9 to 12. So, because that includes 10. Questions, please?
And that's just not gonna be as approximate, because, like, as close to it, right?
It's really tough to predict which one would be best, to be honest. It all depends on how things are changing, so they don't care about that.
Okay.
They just want you to know that to find an estimate of a tangent slope, you can use a secant slope. Okay, give me 1 to 5 is how comfortable you are at estimating tangent slopes using secant slopes, because that will happen later in the packet. 1 to 5, please. How comfortable are you? I'll get back to your calculator in a minute, Stephen. So give yourself another point. Good. Okay, moving on. The actual question, so Mary, this could have been like part A.
Okay.
I just didn't include this.
Yeah.
So. Part B says, sorry, part C. Here's the rate of the water flow. It says use this formula, Q of T, to approximate the average rate of the water flow. Well, Q of T is the rate of the water flow. So they're basically saying find the average of Q of T. So to solve this problem, I'm going to say average, change color here, of Q of T is going to equal 1 over, I'm supposed to do it for 0 to 24 hours, integrate from 0 to 24, I integrate whatever it is I'm averaging, and I do that on my calculator. Because I'm finding the average rate of the water flow, the units will have to be gallons per hour. Okay, Allison, any questions today? Anyone want to ask anything about that? Please, Allison.
Was the DT refused?
Because they're asking me to use this, they want me to find the average of this formula. The DT is actually going to be the calculator's DT, 0.00001.
Okay.
Yeah, so 24 million samples.
Okay.
Now, Allison and everyone else, listen to her question, 2 points. The eyes on the board again, come on. Go, Allison, everybody look up. Look at Kendi for a second. Okay, Allison's question is valid though, because later in the packet there's a problem that says, find the average rate of something, using a trapezoidal Riemann sum. Well, then you'd have to be using this data, and your DT really would be 3,
Okay.
or maybe 6. It depends on how they ask you to divide up the table. That's why I keep telling you, it's perfect, Allison. Keep separate. I need to find an average. What do? I do this. How do I find the integral? Depends. Calculator or Riemann sum. That makes sense?
Yeah.
Perfect. Anybody else? Awesome. Okay. We have 8 minutes. So look at me. We don't have time to do more examples, but there are a few little hints I want to give you. So we're going to kind of go through the packet, and I'm going to give you a few hints. The assignment is this. Finish the packet. Come back to class on Tuesday. No class on Monday, Martin Luther King Day. I'll walk up to your desk. I'll ask you, did you finish the yellow packet? If you say to me, I did everything, but I didn't quite understand that question and this one, maybe a third, I'm good, 2 tickets, okay? But if you say, well, I kind of did it, no tickets, okay? Or like I did half of it, no tickets. Like all of it, 2, 3 questions is kind of normal for this packet. So that's the assignment. Let's give some hints. Number 2. Okay, please read number 2 and just raise your hand if you can think of anything that's coming to mind as to like, wait a minute, I don't quite know what I'm supposed to do, or how do I handle this, or read number 2 and just ask anything you want. Please, Rachel.
So to set it up, at the very beginning, since you're finding the average, you do 1 divided by 2 minus -1, even though it's like that's like just extending 2 plus
Yeah.
1.
Think of it this way, Rachel. The integral starts where they want us to start the average where?
At -1.
Good, and they want us to stop where? Good. How wide is that interval? That's why you're dividing by 3. Okay. Anybody else? Okay, next one. Read number 3. Please raise your hand just like Rachel did if you have anything that kind of pops in your head as to why you might need a hint of some sort. Like Rachel's question was spot on. That's exactly what goes wrong sometimes. People go, wait a minute, how do I handle this negative? No different. No different. Okay, go to number 4, please. I don't want to ask anything about 4. Any part you read that you kind of go, wait a minute, I don't know quite what they mean by this. Nathan. Okay, so you're going to pick up your calculator, but first quadrant, if you haven't remembered, no big deal, we don't use that word that often. Here's first quadrant, here's second, third, and fourth. If you've never seen that before, don't worry about it, it's easy to remember. Okay? If we're in the first quadrant, then when I window, just say it out loud, please. What's my x min? Louder. Yeah, x min is going to be 0. I taught you my best guess for the x max if I don't have a guess. What's my guess? Always 5. So I go 0, 5, I window it. Nathan, I'm looking for this. This curve has, I don't honestly remember the appearance, so I'm going to guess. Maybe something like this. So they want the average in the first quadrant. So they would want you to start here and go here and find the average. Other questions, please.
6, and then they find the x values there in the interval.
Right. If my graph ends up looking like this, I'm going to go from this x to this x. So I'm looking for the average within the first quadrant. So this is how I'm going to figure out. So it's asking for average value. So my brain says, okay, average value. It means I have to integrate from some time to some time, and I have to divide by this. That's how I find average. The key to this problem is figuring out what A and B are. Anybody else? Awesome. Go to number 5. Okay, number 5 is exactly what I was giving you an example with on number 1. They're asking you to find W prime of 12. Look at the table, please. I want you to show me with your hands. We're supposed to be finding a tangent slope of W. Tangent slope of W. That means we use a secant slope to approximate a tangent slope. I gave you an example back here where there were, let's see, 3 different ways to find an approximation for R prime of 12, but only one way to find an approximation for R prime of 10. On this one, please show me with your hands. How many different ways can you find an approximation for W prime of 12? 1, 2, or 3? Show me. So they're asking you to approximate W prime of 12, just like we did on the first one. How many different secant slopes can I find that would approximate this? 1, 2, or 3? Show me. Okay, here's the key to memorize. You're looking for any secant slope that includes 12. So how many different, well, yeah, includes 12. How many different secant slopes can you calculate that basically include 12? 1, 2, or 3? You're doing this, give yourself 3 points. It's identical to the example I gave you.
So if we just could you do 15 minus 0 and then 21 minus 20?
Outstanding. 3 points. Hey, listen to Paris's question. Hey, look at me. Look at me. Come on. It's outstanding, Paris. She said, well, what if I did the secant from here to here? That includes 12. Yeah, they won't actually count that. They want you to get nearby secant slopes. So they're okay going 9 to 15, because it's like the nearest I can get can still include 12. They're okay if I go 9 to 12 or 12 to 15, but they wouldn't want the big jump.
Okay.
Good question.
Wait, also,
Oh, please.
doing 9 to 12, wouldn't that find like 10.5 or something?
much, it would be the same estimate as finding, yeah, it is. It's because they're all just approximations. So it would be an estimate for W prime of 12, but it'd also be an estimate for W prime of 11, W prime of 10, yeah, for sure.
And this one isn't a rate, correct? Because, like, I mean,
The table is not a rate.
table size.
This is back to Ethan's question and Erica. This is just saying the temperature. So like they went out at time 0 and they stuck a thermometer in the pond and go, oh, it's 20 degrees.
So the answer is just gonna be in degrees per day.
Perfect, because you're calculating a rate. Perfect, Rachel. So the result has to be degrees per day. Because you are calculating a rate this time. The other one, we were calculating a rate of a rate. So, okay, next one, 6. Okay, this was Allison's question. They're asking you to find the average temperature of something. So that's the integral, find average. But they command you to do the integral using a Riemann sum. You want to have a follow-up question here. Okay, also in the packet, there are some problems that are just review. They're just, hey, do a Riemann sum. So what I'm doing here is getting you closer to be ready for the test, where I'm starting to mix up the problems. They're not like all the same, they're different. Any questions? Keep going for a second. Bell ring. This one, just like the first one, find the average. This one, this is review. This has nothing to do with average. They just want you to find the value of the integral using a Riemann sum. But instead of giving you a table, they give you a graph. If you know the concept for Riemann sum, you can still do it. It's the exact same concept. Bell's going to ring. Any questions? Good work.